Okay, we're going to cover section 3.8 here, which is derivatives of inverse functions. So first equation we're going to set up here is how to find the derivative of an inverse. So we're going to assume f of x is differentiable and 1 to 1. With inverse g of x equals f inverse of x. Then we say if b belongs to the domain of g of x, and f prime of g of b is not equal to 0, then g prime of b exists, and we get our equation for all this, which is g prime of b equals 1 over f prime of g of b. So we'll do a couple examples, show how this works. Okay, so first example from our book wants us to find g prime of x, where g of x is the inverse. G of x is the inverse of f of x equals x to the fourth plus 10 on domain set of all x such that x is greater than or equal to 0. So before we go much further, what this domain restriction does is it basically guarantees us that the f function is invertible for that region. So x to the fourth plus 10 kind of looks like this. This fails the horizontal line test, so it's not 1 to 1. So basically they're saying keep x equals 0, keep all the positive x's, and throw this part of the graph away. Therefore, you're only keeping starting here at 0. And now this half the graph does pass the horizontal line test, so it is 1 to 1. So it's invertible. So what we want to go through and do here is we want to find, we got f of x, we want to generate the g of x function, and then we'll know what goes in here, and we'll evaluate the f prime. We can get that pretty easily too. So let's, I guess let's figure out g of x. So to do that, I'm going to take the f of x function here, I'm going to replace f of x with y, going to switch x and y, going to solve that result for y. So x minus 10 equals y to the fourth. So the fourth root of x minus 10 is going to equal y, which tells me the g of x function is the fourth root of x minus 10. Now, since our original function f is x to the fourth plus 10. That says f prime of x will be 4x cubed. So now to finish up, we say, all right, well, g prime of x equals 1 over f prime of g of x. So basically, we need to take the f prime function down here, and we need to substitute the g of x equation in for it. So we'll get g prime of x equals 1 over the f prime function is 4x cubed. So I'm going to do 4, create some space, and then it's cubed. And what goes in for that space is the g of x function, which is the fourth root of x minus 10. And that should be our equation. Okay, so that is g prime of x. So we'll take a look at another one of these. I'm just going to do this side example here. It's not in the book. But let's say f of x equaled x cubed plus 3. And suppose g of x equaled f prime of x, or sorry, f inverse of x. And we want to find what is g prime of x. So we're going to do start with the f of x function, switch f of x with y, switch x and y's places, solve the result for y. So we get, solving for y, we get x minus 3 equals y cubed. So we get the cube root of x minus 3. That is y, so that is our g of x equation. To get f prime of x, f of x is x cubed plus 3, so f prime of x is 3x squared. And then when we want to evaluate g prime of x, g prime of x is 1 over f prime of g of x. So it'll be this f prime equation here with the g of x function plugged in for the x. So it's 3 times stuff squared. And then what goes inside there is the cube root of x minus 3. And that's our equation. So we'll move on to a couple other examples from the book and take a look at those real quick. Let's see here. So, second problem wants us to do in the book. Okay, we want to calculate g prime of 1 where g of x is the inverse of f of x equals x plus e to the x. Okay, so g prime of 1 will equal 1 over f prime of g of 1. F prime is easy to calculate. The problem is the switch x and y trick won't work on this equation here. We're not going to be able to figure it out. So what we have to do is say, well, I'm looking for g of 1. So g of 1 equals something. That will mean f of that something equals 1. So I need to think, what could I replace the x's in this equation and get 1 back? And if you look at it a little bit or think about it a little bit, if you put 0 in for the x's, f of 0 will equal 1, therefore g of 1 will equal 0. And then what we need to basically do, that says g of 1 is 0. So this is 1 over f prime of 0. And to figure out what f prime of 0 is, I just need to take the derivative. F of x here is x plus e to the x. So f prime of x, derivative of x is 1 plus the derivative of e to the x, it is its own derivative. So what I get here basically is this will equal 1 over, this right here is f prime. That'll be 1 plus e to the 0. F prime is 0, you just plug 0 in for the x. And this will give us 1 over 1 plus 1, which is 1/2. Okay. So next we're going to get a whole bunch of derivatives of arcsine functions. And so what we're going to do for those is we're just going to write all the functions down first. And then after we write all the functions down, we'll go through and just do a bunch of examples. And these usually on the AP test, these get mixed with the chain rule a lot. So we got d dx of arcsine. That's going to equal 1 over the square root of 1 minus x squared. And the derivative of arc cosine that's going to equal the negative of this value. Okay, so that's the first two. We need to cover tangent and cotangent. I'm sorry, arctangent. That will equal 1 over x squared plus 1. And that will equal negative 1 over x squared plus 1. Then we need to cover secant and cosecant. So arcsecant is 1 over absolute value of x. And then it's times the square root of x squared minus 1. And this will equal negative of that. So these are your 6 arc-trig functions. We're going to refer to them for the next group of problems. And we're going to kind of mix these together with the chain rule. So we'll do about 3 more examples of these and then say that that's good enough for the section. So first example, we'll say, what is d dx of arc cotangent of x squared plus 2 to the x? Okay. So what we got to do here is we have to take the derivative of arc cotangent, which to do that we'll use this formula here. But instead of the x here that's squared, the chain rule is going to apply here, so we'll leave the inner stuff here alone. And then we have to multiply by the inner derivative, so we'll multiply by the derivative of the inner part. So to take arc cotangent's derivative, I get that this is negative. It's going to be 1 over stuff squared. It should be plus 1. So we get negative 1 over x squared plus 1. But in what we have here, we're not going to put x in there. We put the inner function here. Put the inner function there, and we leave the inner function left alone. Then this gets multiplied by the derivative of the inner function. The derivative of x squared is 2x. The derivative of 2 to the x is natural log of 2 times 2 to the x. And that will be our derivative. So I'll do a couple more of these. Next example, suppose we wanted to know, let's say f of x equaled arc cosine of, let's say, x cubed plus sine of x. We want to find f prime. So we say, okay, first of all, I need to take the derivative of arc cosine. That's the outermost function, so the chain rule is going to apply here. So I'm going to take the derivative of the outermost function, and I'm going to use that equation, and I'm going to leave a blank where the x used to be. So if we look at arc cosine's derivative, it's negative 1 over the square root of 1 minus x squared. So we're going to say this is negative 1 over the square root of 1 minus, I'm going to create some space and make that squared. What goes in here is the inner part left alone. So that'll be x cubed plus sine of x. Then you need to multiply this whole bit by the derivative of x cubed plus sine of x, which is 3x squared plus cosine of x. And that will be our derivative. So final example we'll do is from the textbook, and then we'll say that that's good. This is example 5 from the book. And it says calculate d dx of arc cosecant of e to the x plus 1 of e to the x plus 1, and we want to know what all that is evaluated at x equals 0. So first step is we're going to figure out what's the derivative of arc cosecant of e to the x plus 1. So we're going to use arc cosecant's equation, and we're going to replace the x in it with the inner part here, e to the x plus 1. So arc cosecant's equation is negative 1 over absolute value of x, square root of x squared minus 1. So we'll say, okay, this is negative 1 over, I'm going to create a spot for where the absolute value of x was, times the square root of the absolute value, or create a spot where the x used to be, minus 1. Double check, make sure I didn't mess that up. So basically where these two x's are, we're creating a spot there, and what goes in the spot is e to the x plus 1. Then what we do is we multiply this by the inner derivative, which is the derivative of e to the x plus 1. E to the x is its own derivative, and 1 has derivative 0. So we just get this. And now basically we just need to go through and replace all the e to the x's. We need to just plug zeros in for the x. So we get that. This will be negative e to the 0 is 1, so that'll be over absolute value of 1 plus 1 is 2. Square root of 1 plus 1, which is 2 squared, which is 4, minus 1, which is 3. So that'll be negative 1 over 2 square roots of 3 for our answer. Okay, and that's going to wrap that section up. So we'll stop there.